All right, today we're going to talk about how to build a digital brain. No, seriously, we're diving into expert systems, one of the earliest and honestly one of the most practical applications of AI. It's a really fascinating contrast to the machine learning models we hear so much about today. So let's get into it.
Just think about it for a second. What if you could take decades of a specialist's hard-won knowledge, a doctor, a master mechanic, a geologist, and just make it available on demand for anyone, anywhere in the world? That is the fundamental promise of an expert system. It's really all about bottling expertise.
So, what are we actually talking about here? Well, at its core, an expert system is a program that's designed to mimic the decision-making ability of a human expert. And it does this with two key ingredients. First, a massive library of very specialized knowledge, and second, a really powerful engine for reasoning. To really get this, we need to pop the hood and see how this digital expert is actually put together. I mean, how do you even begin to construct a digital mind?
Okay, so to make this all super clear, we're going to follow one single, very practical example through this whole explainer, a system that helps a mechanic figure out what in the world is wrong with a car engine. It's just a perfect way to see all the moving parts in action.
All right, let's dissect this digital brain. Every single expert system is built from just a few essential components, and they all have to work together perfectly. Let's break them down one by one.
First up, you've got the knowledge base, and you should really think of this as the system's brain. It's the library. It's where all the specialized facts, the figures, and the logical rules for one particular area, like, car repair, are stored. Now, this knowledge isn't just a big pile of data. Nope, it's very strategically split into two parts. You've got a database of raw facts, like the normal temperature range for an engine. But then you have the rules base, and this is the key. It's got these simple but incredibly powerful if-then statements that copy how an expert thinks. So, for example, if the engine temperature is above 220 degrees, then trigger an overheating warning. Simple as that. So if the knowledge base is the library, then the inference engine, well, that's the super smart librarian who actually finds you the answers. This is the active thinking part of the system. It takes the user's problem, it searches that knowledge base, and it applies all those if-then rules to come up with a logical conclusion. And of course, you need a way to actually talk to this digital expert, right? That's the user interface. It's just the screen, the keyboard. It's how a mechanic inputs the car's symptoms and gets back a list of possible causes. It's the communication channel. But look, these systems don't just build themselves. That's where the knowledge engineer comes in. This is the human architect. This is the person who interviews the real-world experts, structures all their knowledge into facts and rules, and basically builds this digital brain from the ground up. And this just shows you the whole process beautifully. The mechanic types in, hey, there's a rattling noise, and the check engine light is on. The inference engine grabs that, searches the knowledge base for any matching facts and rules, and then spits back a recommendation, high probability of a faulty oxygen sensor. And here's why. Now, this is where it gets really cool. That inference engine, the thinking part, is actually pretty sophisticated. It doesn't just follow one rigid path of logic. It can actually think in two completely different ways to solve a problem. Let's explore what those are. The two big methods are called forward chaining and backward chaining. So forward chaining is data-driven. It starts with the facts you already have, and it works its way forward to a conclusion. Backward chaining, on the other hand, is goal-driven. It starts with a possible conclusion, a hypothesis, and it works backward to see if the facts actually support it. A great way to think of forward chaining is like a detective showing up at a crime scene. The detective doesn't start with a suspect. No, they start with the clues, the data that's right there, and they follow that chain of evidence step by step until they reach a conclusion about who the culprit is. It's a total bottom-up approach. Backward chaining is pretty much the opposite. It's more like a doctor doing a diagnosis. The doctor starts with a hypothesis, a goal. I think this patient might have the flu. And then they work backward, looking for specific symptoms like a fever or a cough to either confirm or deny that hunch. Our car mechanic system, it would almost definitely use this method. So the really crucial point here is that these systems are incredibly versatile. I mean, they're not just for fixing cars. Let's look at a few real-world examples to see just how widely these things are used. The most classic example has to be in medicine. An expert system can act as this incredibly powerful diagnostic assistant. It takes a patient's symptoms and suggests a list of possible diagnoses for a physician to consider. And this is a total game changer, especially in remote areas where specialists just aren't around. They're also used in some really high-stakes fields like geology.
A system can analyze rock types and seismic data from a site, compare it to models of successful mines, and spit out a percentage, a probability of finding a particular mineral or oil deposit. This helps companies avoid multi-million-dollar mistakes. Over in finance, these systems are helping to democratize expert financial advice. A client just answers questions about their income, their goals, their risk tolerance, and the system uses its rule base to recommend a totally tailored investment strategy. It makes sophisticated planning so much more accessible to everyone.
And you've almost certainly seen them in action in the video games you play. An expert system, often using forward chaining, helps a non-player character, an NPC, make smart decisions on the fly. It analyzes the data, distance to target, enemy type, and uses its rules to pick the best response, making the game that much more challenging and immersive.
And really, that's the whole idea. The goal was never about replacement, it was about empowerment. Expert systems are designed to be powerful assistants, to capture, scale, and share specialized knowledge. They allow more of us to make better, more informed decisions. Which kind of makes you wonder, right? As this technology gets even better, which decisions will we still need to make for ourselves?